Romali ma'am, is it audible? Romali ma'am, is it audible? Can you hear me?
Yes sir. Yes sir. Yes sir. உங்களுக்கு கேக்குதா நான் பேசுறது?
Yes.
Is it audible sir?
Audible ma'am. Audible.
Okay sir. Okay.
Audible. மேம் இப்போ மியூட் பண்ணிக்கோங்க.
ஓகே சார். ஓகே.
Hello, Praveen.
Nicholson.
Siddharth.
கேக்குதா? ஹலோ.
கேக்குதா?
கேக்குது கேக்குது. கேக்குது. ஓகே. இப்போ ஷேர் பண்ணலாமா?
ஜஸ்ட் பவர் பாயிண்ட் ஓபன் பண்ணி வச்சுக்கோ.
ஓகே. அப்ப நான் இதுல பிரசன்ட் நவுன்னு கிளிக் பண்ணுமோ?
ஆமா.
ஓகே.
பிரசன்ட் நவ் கொடுத்தே வச்சுக்கோ. பிரச்சனை.
சரி சரி. எனக்கு ஸ்கிரீன் தெரியுதா? என் ஸ்கிரீன் தெரியுதா?
தெரியுது.
ஓகே. என் பேசும் தெரியுமா?
ரெண்டு இதாக தெரியும். ஒன்று வந்து பர்சன்டேஷன், இன்னொன்னுல வந்து வீடியோ.
ஓகே ஓகே. இப்போ என் பேசும் தெரியுதோ?
இல்ல, ரெண்டு தெரியும் இல்லையா? அதுல பேஸ் தெரியறத வந்து அப்படின்னா பேஸ் தெரியும்.
ஓகே
தெரியும்.
ஓகே. அது நான் தான் பண்ணணும் அப்படிதானே? ஓகே.
இல்ல நீ அப்படியே இருக்கட்டும் ஒண்ணுங்க.
ஓகே. இப்ப ரெஜிஸ்டர் பண்ணவங்களுக்கு எல்லாம் லிங்க் வந்து நீங்களே அனுப்பிச்சிருவீங்களோ? அது எப்படி?
ஆமா, எல்லாருக்கும் அனுப்பிச்சு.
எல்லாருக்கும் அனுப்பிச்சாச்சு. ஓகே.
ரியோ கிளாக்ல தானே, அதனால கொஞ்சம் இன்னும் வருவாங்க.
சரி.
ஷேர் விண்டோ கொடுக்குறாங்க. Praveen?
Yeah.
Just stop presenting and try to share the window.
Okay.
Share. நீ என்ன கொடுத்த?
Start presenting கொடுத்தேன்.
Full screen கொடுத்தியோ? Share screen கொடுத்தியோ?
Yeah.
Share windowன்னு ஒரு ஆப்ஷன் இருக்கும், அதை கொடுத்து. First stop பண்ணு. Presenting stop.
Okay.
Okay, it's enough.
Okay. Okay.
Praveen, let's wait for another 5 minutes. Okay.
Okay. Okay, right.
Okay, exactly at 3 o'clock.
Okay, right.
Right. Praveen, you can mute yourself now.
I can move to?
Mute yourself.
Ah, okay.
Okay, welcome you all for this webinar. It's a time to welcome. It's indeed a pleasure for me to welcome you all for this webinar series, NEC Science and Humanities WEBTALKS-2K20. First, I would like to welcome our resource person, who is my classmate in BSc, Dr. Praveen Devadev, postdoctoral researcher, Israel Oceanographic and Limnological Research, Israel. Welcome you, sir. Then I welcome our Head of the Department of Science and Humanities Department, Dr. M.A. Nilakandan, for this webinar. Welcome you, sir. Now I welcome all my colleagues of National Engineering College. Welcome you all. Finally, I welcome all the student participants, faculties, research scholars of various institutions and industry peoples for this webinar. Once again, I welcome you all. Thank you. Now I request our Head of the Department, Dr. M.A. Nilakandan, to say a few words to start this webinar.
Thank you, Dr. Nicholson.
Yes, sir.
I will start so all the time or the birth plan execute the series in a plan or in a particular definitely many that the one I said the top where plan so we benefit these feedbacks I received. This program organized the topics I recall participants and faculty members actively program. The resource is research from geographic and from Israel and
Voice is not audible, sir. Not clear, sir.
okay, I will this program because it is not strong. Thank you, Nicholas.
Okay, sir. Okay. Thank you, sir. Thank you for your kind words. Okay, now I request Dr. P. Gomadi to introduce the resource person.
Good afternoon to all. I have very pleasant duty of introducing our resource person, Dr. Praveen Jabadev. He did his BSc and MSc Physics in Scott Christian College, Kanyakumari, and MTech in Remote Sensing from Anna University, Chennai. He has received his PhD in Ocean Remote Sensing from Indian Institute of Technology, Madras, in the year 2017. Now, he is doing postdoctoral research in remote sensing and acoustical laboratory, Israel Oceanographic and Limnological Research. In the year 2009 to 2011, he worked as Assistant Professor, Department of Applied Geophysics, Manonmaniam Sundarnath University, Tirunelveli. He has served as research scientist at National Center for Sustainable Coastal Management, Ministry of Environment, Forest and Climate Change, Chennai, in the year 2017 to 2019. His research focuses on radiative transfer in the ocean and atmosphere, theoretical modeling and experimental studies in marine optics, microwave and ocean color remote sensing, underwater imaging, satellite image processing and analysis, and algorithm development. He has published more than 15 research papers. Today, we are privileged to have an opportunity to listen the current topic on remote sensing and its applications. On behalf of all gathered here, I welcome you, sir.
Thank you for welcoming Dr. Nicholson and Head of the Department of Science and Humanities Department. And a very good afternoon, everybody. And I hope all are fine during these tough times. And I'm very glad to see a lot of people have registered in this lecture, and I'm very thankful for Dr. Nicholson to inviting me for this lecture. And more specifically, today I am going to present about remote sensing and its application. And generally, I just want to focus on the most generalities. As I just briefly, I saw the registered people who are mostly from computer science and ECE backgrounds, and so I restrict myself to the more into the details of how remote sensing works and how it can be useful for the students and faculties, and what kind of researches that can be done for the benefit of the mankind and other things, and what is going on in the current in the world, and how one can do and one can take up this research of remote sensing to the another level, and what a student can contribute to the remote sensing. And currently you can see daily, you can see lots of satellite launches per day. Even China is launching a number of satellites per month, plus more than 5 to 10 satellites per month, and even NASA is launching plenty of satellites. And currently even we see lots of even satellite debris around, even we see all the time in the newspaper. So remote sensing is becoming a popular science, and to explore the Earth, not only exploring the Earth, also exploring the other planets, and what is there in the other planets, how to use the resources, and all this comes into a single domain called remote sensing. So basically, a basic understanding of remote sensing comes from understanding some physical concepts of physics, some physical concepts of basic electronics, and basic applied sciences. It could be earth sciences, it could be planetary sciences, it could be anything like interplanetary and also earth domain. So basically, I just want to restrict myself today about remote sensing, what the launching companies are doing, or the launch governments are doing, and how they take the remote sensing research to the next level, how it is useful to the mankind, and those things elaborated way. I just want to make a brief generalities. So let us restrict ourselves with generalities of remote sensing. And first, I just want to talk about what are the Earth absorbing satellites presently available now. So there are, even though remote sensing is used to detect other planetary materials, objects, and what are the mineral resources in the other planets, and it is still a lot of things have to be done on the Earth itself. Even our Earth is not fully explored. So in that sense, when we are talking, even we have launched several Earth absorbing satellites. NASA is launching several satellites per year, China is launching, India is launching, European Space Agency is launching, and several space agencies are keep on launching satellites. But these launching, we see in papers about the launching of the satellites, but after launching, there are many other things, like it retrieves the data from remote sensing. We get some data. So what kind of data we get? We get in kind of images. So we have to process those images, and how the image is, the information is, how the data is acquired, what kind of imaging systems are used to detect those objects, and how the data is, that the image, how it is stored, how it is compressed, and how Fourier transform are used, and how it is atmospherically corrected, and how algorithms are developed. For example, if there is something in the Mars. Let us say some resources are there, some minerals are there in the Mars. We need to detect from the space because we cannot go directly to the Mars or other planets to get some information. So basically, we rely on satellites. We rely on the satellite data. So data extraction, data interpretation, data analysis, these kind of things are very important. So basically, I will just give an overview of remote sensing on Earth observing. I'm not going to deal with the planetary sciences. I'm just going to deal with the Earth observing platform. Basically, since I am an expert only on oceanic sciences, so I will just deal with a little bit of land things. But however, as a generality, you can understand what is happening in the remote sensing. And when you understand the remote sensing basics, even every student or faculty or any member can contribute to the remote sensing community. For example, India is much booming. India is much growing in the field of remote sensing, and we have several national institutes in terms of remote sensing agencies. We have in Hyderabad, we have in ISRO, we have in Ahmedabad, we have in several places. We have around the world. We have every state has a remote sensing agency. Even in Anna University, we have a center called the Tamil Nadu Remote Sensing Center in Anna University. So it is very so even the citizen sciences, even students and other even faculties can contribute through their contribution through research, and we can take it to the next level. So basically, first I just want to tell what is remote sensing. Remote sensing, to learn remote sensing, you need a little, and I told that you have to know something about basic physics, how light works, how light interacts with the matter, and some basic understanding of mathematical basic equations, and some geological, some instrumentation, how light interacts, how signal is processed, how data is processed, how image is acquired, how you can interpret data, those kind of things you can, that understanding basically you should have. So coming to the point, what is remote sensing? Remote sensing is a technology that you can detect physical characteristics of a target from a distance. That is, without an actual contact, we have to get information, that is getting information from a distance, that is called remote sensing. Either it can be anything. Mostly it is measured from satellite and aircraft. As a first figure you can see, there are two types of remote sensing. One is called passive sensor remote sensing, and another is called active sensor remote sensing. What passive sensor does is, this is the satellite sensor. You can see the first image. It's the satellite sensor. It just want to collect information of the ground object. So it uses the sunlight. When the light from the sun hits the target, and it gets reflected, and the reflected signal is captured by the satellite. When it uses the sun as the source, then we call it as a passive system. And if the satellite itself has a transmission signal, it itself sends a signal and it captures the return signal, that is called the active system. Mostly passive system is optical remote sensing. We call it optical remote sensing, and the active system we call radar, microwave remote sensing. And generally, optical remote sensing is more even both are useful. So optical remote sensing have more day-to-day life applicability. So today we will talk about most passive systems, that is optical remote sensing. Okay, then why do we need it? Why do we need it? How that is applicable to day-to-day life? So generally, who can work on remote sensing? I told you that we need some basic understanding of light, we need basic understanding of matter, how light interacts with the matter, how it reflects, how it absorbs, how it backscatter, all those things, basic science you need. Plus, you need some understanding of little programming and little mathematical knowledge, and plus you need some instrumentation, how to detect it, how to process it, how signal is transformed from one form to another, and those things you need to know. So basically, if this knowledge is acquired, one can easily apply to the several. This is applied in several numerous fields. For example, it is applied in earth science, it is applied in climate science, hydrology, ecology, meteorology, oceanography, glaciology, geology, geography, land surveying, and also it is used for military, intelligence, weather forecast, commercial, economic, planning, humanitarian, and many more. Even many things I have not described here. Even there are many other applications, and astronomy. Even many things are happening. You see, we launch satellites to the moon, and we generally monitor moon, and even it is used in military resource management and many things. And so basically we need some understanding about the basic understanding of light, matter, instrumentation, and little of programming. So basically, who generally uses, primarily runs and uses this technology? Since remote sensing is as a person, as a group, as a single person, one cannot run a remote sensing technology. So many people from different fields, for example, from electronics, from computer science, from physics, from chemistry, from biology, from earth science, from climate science, from astrophysics, many people come together and work to bring up this technology. So the most famous space agencies I have listed here, even I have listed only the governmental agencies, even private agencies are there. Even recently you can see the Elon Musk, recently SpaceX has launched a satellite, and recently they want to go to Mars. However, we don't know whether that is happening or not, but still there are very few agencies that are keep working and progressing very faster. For example, NASA, European Space Agency, Russian, Indian Space, ISRO, Japan Space Aerospace Exploration Agency, Australia, China, Israeli, and other Korea, Canada, etc. There are many agencies are working toward this, and they have lots of centers around the world. So basically, I will limit myself to the Earth observing satellites. There are few satellites. I have just put only the few sensor satellites. There are many other satellites, but there is no space. That's why I just made a little bit. So these are all launched for the benefit of mankind, to forecast the future and what kind of utilization can be useful for the mankind, and other things can be done using this. So as a basic thing, the first NASA launched a satellite called Landsat in 1972. So it was much long ago. Even I was not born at the time. Basically, since 1972, there are much progress in the satellite remote sensing technology. First, Landsat 1 was launched in 1972, and the operation was ended in 1978. Then Landsat 2, 3, 4, 5, 6, 7, 8, and currently 9 has been launched. 7, 8, and 9 is in operational. This is the most successful satellite mission ever. For example, we use Google Earth, and all the things have been brought from the understanding of failure, success of Landsat satellite missions. So satellite is the most popular thing in the world. And the next, when you come to ocean and land sciences, MODI satellite, moderate resolution image spectroradiometer, was one of also most successful satellites, which was launched in the 1999, and that Terra was launched in 1999, and Aqua was launched in 2002, and till date it was working. It was originally planned to run for 5 to 7 years, I think, but still it is running more than 20 years. So it is keep daily data. It is giving upon data, and still we are using the MODI satellite, one of the most successful oceanographic and land-based satellites. And VIIRS, this is also another satellite that is mainly for infrared imaging. That was used to understand the climate science, how clouds form, how aerosol work, and to find the surface temperature, whether the sea level is rising or not, whether to determine the forest fires, whether there are El Nino, there are many other oceanographic processes. This VIIRS sensor was very successful in that. And one of the most popular, and recently it is not in operational, but it was a famous satellite, HICO satellite, Hyperspectral Imager for coastal ocean. It was launched in the International Space Station, and it took lots of data, for example, coastal data, land data, cities, and it was monitoring several times, and it is now another mission is coming, PACE mission. So it is a prototype sensor which is used for the upcoming PACE sensors. So basically now we have seen an overview of remote sensing, how these things are happening, and how what in remote sensing, and it's a much booming technology, and any people can contribute to this research, and even many satellite images are there still available on the internet, and even you can register, and for research purposes the NASA is providing lots of images for free. So we have to register as a student, or we have to register as a, if we are an academic institute, it is much easier, so that you will get a lot of data. But if a private company will not get any much more data, so you have you have more what to say, you have more advantage. You have more advantage, so you can register with your ID card, and they will provide you the data. Only thing you need to know how the system works. So basic understanding that will let us see in this presentation. I'll make it very short. First, as an understanding, I told that we need an understanding of light. So what is light? Light is light means, we can say it is as a electromagnetic radiation. Electromagnetic radiation means we have a very large range of radiation. In that big radiation limit, visible light is a small portion of it. You can see here, these are all range or radio waves, microwaves, and then comes infrared rays, then comes visible light. Visible light, you can see the entire wavelength. You can see the very small portion of this is called visible light. We today will deal only with visible light, that is optical remote sensing. There are micro remote sensing, radar remote sensing, and there are infrared remote sensing, but we'll stick to optical remote sensing. And even ultraviolet is there, even ozone, those lot of things we can detect data, and X-rays and gamma rays, but we'll stick to the optical remote sensing. This is the classification of electromagnetic radiation. Our ultraviolet, all things you can see here wavelength and its frequency, but let us see, we'll focus only to the wavelength 0.4 to 0.7 micrometer. First, as an optical remote sensing, we rely on the sun as a source of light. So, sun gives energy. So, with the use of sun, we detect the reflected sunlight. So, the reflected sunlight gets the information. It has the information of the target. So we get the target and then we interpret. So basically we need to know about light and black body radiation. For example, if you have a radiometer, that means radiometer is an instrument which can measure light. If we have a radiometer and we focus to the sun, it can measure the incoming photons. If we measure the incoming photons, and if you just plot in a graph, it will be something like this. 0.1 to 100. If you see in this visible range, 0.4 to 0.7 micrometer, you can see the visible light. This is the incoming light from the sun. How do we estimate the spectra? Just by incoming the number of photons. And one thing I just want to tell that how to estimate the temperature of the sun by the incoming photons. We cannot go to the sun to measure the temperature, but what one can do, what is coming from the sun, we can measure that and we can estimate the temperature of the sun. Same way applies to the other planets. Even it applies to the Earth, it applies to the moon, and it applies to any other planet, any other solar system in the space. So basically, the first person who estimated the temperature of sun and other planets and other galaxies is the Stephen. The first, what he measured is, he just measured the incoming photons. That is the total energy coming from the sun. That is called the E. He said that the E is proportional to the 4th power of temperature. If you see in this plot, you can see the sun has 6,000 Kelvin degrees Celsius, and you can see the Earth here is 3,000 Kelvin temperature. That is approximately 15 degree as an average. From polar to the equator, you have an average temperature of 15 degrees Celsius. Average temperature of the Earth is 15 degrees, 300 Kelvin. So he was the person who first estimated the temperature of the sun. Based on that, the Wien's displacement law, the Wien's came and said that if the wavelengths, that the temperature measurement can be found by the displacement of the wavelength. If the spectral radiant flux moves around the wavelength, so we can see the spectral peak. Using the spectral peak, we can able to find the temperature of the planet or a sun or anything else, even in the Earth. So comparing all these things, Planck estimated another equation as a function of a wavelength, as a function of temperature, which is the combination of the Stephen's law and the Wien's displacement law. Basically, Planck's radiation law is more accurate than both of the previous laws. So this is a black body emission of the sun and the Earth. For example, this is the black body spectrum of the sun, and this is the black body spectrum of the Earth. Based on the photons received, based on the radiative flux, based on the energy, we can estimate the emission, incoming energy of the sun or any planet. So first, now we saw about the source of light. So next we shall see about the sensor related thing. Anyway, these are the sun components. Nothing is there to learn more now, but there are many other things related to the sensor and the images. So basically, remote sensing is a study, just interpretation of the digital images. So, but how does it differ from normal photography and the satellite imagery? We don't say satellite as a photograph, we say satellite as an imagery, satellite imagery, we say like that. But as a normal camera, we take as a cell phone, or we take in a digital camera, we just say as a photograph. So how does that differ? So there are some differences. I'll tell you how the differences. The left side, what you are seeing is the green scenery photograph, is a photograph by a digital image, and the right side, what you are seeing is an image by a satellite sensor. But this is both are RGB. It's both are the combination of red, blue, and green. Because our eyes, our human eyes have a photosensitive things in our eyes. So this can understand only the combinations of blue, red, and green. And though that bandwidth is a little bit bigger, smaller, depends upon person, and it depends upon the cones present in the eyes, we just rely on the red, blue, green wavelengths. So as a combination, we can, the size of the normal digital photograph is around 0 to a few kbs to 500 kb. It's a maximum. But when you come to satellite image, you will have a very large size from 0.6 to 1 GB and even more. Even hyperspectral images will have much more, even 4 GB, and if radiometric resolution increase, it will be much higher. But actually, our camera is much the satellite sensor is much different from a normal camera. So let us see how does a satellite see the Earth. This is the typical image. You might have seen this image in Google Maps or something that I just downloaded from Sentinel. This is imaged by satellite Sentinel 2 satellite sensor, imaged of Rameswaram region, and you can see the satellite does not see just only on a single wavelength. It measures light in all the wavelengths. Previously we just saw light starts from 0.49 micrometer to 0.7 micrometer. It measures in every band. So the NASA or ISRO, when they developed a sensor, they used to keep a certain wavelength bands to sense the ground. So accordingly, in each band, it captures the image. For example, in case of this image, what you are seeing now is a Sentinel 2 satellite image, which measures in 12 bands. First, you can see 5, and here 2. So it measures in 12 bands, and based on but it all looks like black and white. It is not at all a color. It does not seem a useful image for us. But after processing, this can give us a useful information. So to convert to useful information, we know some basic understanding of light, how it is captured, how it is stored, and how to interpret. The last two figures here, the false color and true color. True color is a combination of band number 2 and band number 3 and 4. This is a combination of red, blue and green. So here it is almost looking like a RBG. It's a normal, it looks like a normal photograph. Actually, it is not a actual photograph. False color is, for example, if you want to differentiate from one material to another material, or you want to differentiate one type from the another type, you can play with the bands. So by playing with the bands, you can generate and you can detect in other objects. This is for Earth, and similarly it can be applied for other planets, so that you can find out the resources. If some other resources are there in the planet, we will be able to easily find it. So, but why NASA or ISRO, they have lots of bands in there? Because each band has a specific information. But a normal photograph does not have any specific information. It does not contain any scientific information, does not contain any physical parameters. But a satellite image has many other physical parameters. You can do science with that, but with the normal photograph, you cannot do any science. So band 1, you can see this is a typical of Sentinel 2 multi-spectral imager. I will come to the multi-spectral imager later, but here you can see band 1, B1, B2, band 1, band 2. There are certain bands, some bands, and it contains certain information in that. So band description, if you see, it contains about the aerosols. Aerosols are the dust particles or the particles, oxygen or some other particles that is floated on the atmosphere. So these kind of particles can be captured in the band 1, that is within the 400 to 450 nanometer. So similarly, band 2, whatever blue, for example, water, ocean detection, ocean changes in the ocean, everything you can detect using the band 2. Band 3, whatever the things, for example, if there is a ship coming, enemy ship coming, we can easily detect using the green and the red band. And for example, if any submarine coming, even you can detect it, even though it is not optically, light does not much penetrate, but still there are many other indirect influences of things you can measure through the internal waves. There are many other things. And even red, and for plantation vegetation, they use band 5, 6, 7, and near infrared and thermal. If there's forest fire, there will be big change in the thermal. For example, if a volcano is going to explode, you can find out in the thermal infrared regions. Similarly, for clouds and major things, each bands are specifically useful to interpret the and to infer some physical data. And now let us come to the instrumentation type and how does a satellite sensor work and what are there in the systems. So basically, if you talk about a satellite, it will be a 4-type imaging system. Either it will be a panchromatic imaging system, or it will be a multispectral, or superspectral, or hyperspectral. So first, let us see the panchromatic imaging system. This panchromatic imaging system is just a black and white image. It measures in a single wavelength band, B1, a single band. So it contains only 2 values. Either it will be 0. It is a digital image, so it will be either 0 or 1, or a variations of 0 and 1s. So it will be a black and white image. The right side, what you are seeing is a ICNOS image, and it is a black and white. It is high resolution image, and it will give either 0 and variations of zeros and variations of 1. So this is the panchromatic image. And the next, multispectral system. Multispectral means, spectra means color. So multispectral means you have more colors. So band 1 to here you can see band 1 to band 7 means you have 7 colors, and with these 7 colors you can make combinations of blue, combinations of green, and combinations of red. With this you can make a final form which according to your use. If it is a military use, they will be using according to their application. If it is a climate science use, they will be using according to their applications. And next, superspectral. First we saw panchromatic, it was a single band, and the multispectral has a little more bands, but superspectral contains little more bands, several bands. If your spectral bands increase, then your data quality will also increase. currently we are in the state of currently, according to the current technology, we are almost in the super spectral and high. We are just passing to the hyperspectral. There are a few satellites have been launched in hyperspectral, but lots of failure has come. So now they are learning from the mistakes, and now we are developing a new hyperspectral system. The next decade, we will be having a very good hyperspectral systems in the upcoming decades. So hyperspectral contains more spectral bands. This is a hyperspectral image. Last time we saw panchromatic only one band, multispectral we have 7 bands, superspectral we had more than 10 bands, and hyperspectral we have more than thousands of bands. So if we have more bands, we can extract more information and we get lots of data. So we finished about the image systems. So any satellites, for example, if you talk about a Sentinel satellite or Lancet satellite, either it will be a multispectral or a hyperspectral. Now coming to the image. So first we saw about light, next we saw about the sensor type, and now we can come to the image, because the sensor captures the image. Now after acquiring the image, now we have to interpret the image, how that is useful for the day-to-day life. So that comes, there are 4 things we need to be care of. First, spatial resolution. Second, spectral resolution. Next is radiometric, then temporal. So let us see what is spatial resolution. Space means we know it is a X and Y dimensional. So X and Y, you can see the image. For example, first image, you can see the clarity is very good, and the clarity is very decreasing in the next image, and so on. So what is a spatial resolution? For example, spatial resolution is a resolution which a single pixel contains a minimum ground truth distance. If we have information of a smaller distance, then we call it as the image as a high spatial resolution. So it can give a data of even a small portion. So if the spatial resolution decreases, then your quality of the image also decreases. The first image you can see is 0.5 meter resolution. So the satellite can see the 0.5 meter very clearly. The next image is 1 meter. So the satellite can see 1 meter depth distance. And second, we can see the 2.5 meter distance. Similarly, more the spatial resolution, more clarity is the image. This is an example image taken by the PDS satellite. And this is also applied previously. This is applied for cadastral mapping and urban planning and all those things governments are using. All governments are using, even India. Lots of things have been done in the recent years. And similarly for climate science, you can also use those high spatial resolution data for climate sciences, like detecting volcano and detecting shapes and so on. And now let us come to the spectral resolution. Spectral resolution means the differentiation between the ability to describe between the wavelength bands. So more spectral bands if you have in an image, you will have more information. So you have the more, it will sense in the more narrower wavelength bands. So you can get more color information. And next we shall come to radiometric resolution. Radiometric resolution is, for example, I'll make it as simple. I'll just tell. For example, let us compare with our eyes. Let us see. We can able to see only white and black and white. So what does that mean? We cannot differentiate between the object. We cannot differentiate between the red and the green. So if we can differentiate only between black and white, then that means our eye sensor is capable of seeing 1 bit. So 2 colors. So here the right hand side you can see 1 bit resolution contains 2 colors. Here I have put in color, but actually you can see black and white. There are 2, either 0 or 1s, because computer understands only 0s and 1s. So single bit means just 2 colors. So if you increase the bit colors, if the sensor can able to see more variations in the color, then automatically your radiometric resolution increases. If you have a 3-bit resolution, you have 8 colors. If you have 6-bit resolution, you have 64 colors. Likewise, it increases the 2 power n. it increases in the form of 2 power n. So when you increase this spatial radiometric resolution, your size of the image will increase exponentially. And this is the typical example of radiometric resolution. The first bit you can see only combination of 2 color, see either 0 and 1, and next is 4 color, 16, and finally you can see the clarity of the color, clarity in color, that is called radiometric resolution. And temporal resolution is nothing related to the sensor thing, it is related to the general open area. For example, for 1960 there is an image like 1973 there is an image like that. 2000 there is, so yes, the urban has developed very much, and 2006 you can see the difference. So the same sensor captures image throughout the time. So that variation in the time that is called temporal resolution. Okay, now the image. Let us come to the data levels. How the data is stored. Most of the computer science students might have studied in their basic image processing levels, and there are in satellite things. There are several levels. There are certain levels: level 0, level 1, 2, 3, and 4. Level 0 is the basic minimum level. That is what it's a raw radiance. We call it as a raw radiance. Raw radiance means it will just capture a basic. It will just capture the incoming light. That's all. You will not know what is there. It is form of some digital counts. So now we have to convert this digital counts to the meaningful scientific units. So to convert into the meaningful scientific units, there are several levels of processing. So to do this work, you need a strong basic knowledge of programming, and you need some strong understanding of light correction methods. So as a combination, as of level 0, from raw level, you can convert to the level 1. So you have a next order data with basic calibration, pre-launch calibration, calibrate. All these basic calibrations will be done in level 0, and then it will be converted to level 1. From level 1, other corrections, for example, atmospheric corrections, and these kind of corrections are done. And for atmospheric corrections, there are another set of people who works on atmosphere, who work on earth science. They come and they do, because they know the physics of the climate, the physics of the atmosphere, the physics of light, how the light interacts, how the light scatters, how the light backscatters. That is a solid physics. So those people come and they develop atmospheric correction with the programming knowledge. Even you need the strong knowledge in programming to do all this stuff. And next, after that correction, then directly those who users will come. Those who the research, for example, research geophysical, those who work in geophysical quantities, who works on a climate, who works on the sea surface temperature, who works on land temperature, who works on vegetation, forest, etc., etc., etc. And those people use the level 2 data. And the final level, level 3 data is the data after processing with level 2 that is openly kept for the open general public, and it is applicable for operational applications. So these are the levels. You need to just know how systems work. That's all. So that is the one thing. So we saw about data level processing. Now let us come to image compression analysis of the satellite imagery and how Fourier transforms are used in remote sensing. So basically, most of us have studied Fourier transforms and how it is applicable in remote sensing. Let us see shortly. I will not take much time, but I will just will go through. So basically, Fourier transform was basically developed by Fourier in 19th century, previous century. But at that time, nothing was there. There was no remote sensing, no image, no photography, or nothing. But he did for signals. Same thing can be applied for the image, and let us see how it is applied to the images. So in terms of images, it is used for data compression and image filtering, image reconstruction, image analysis, cutting off, chopping off, and filter, bandpass filter, a lot of other things are there. We can work with Fourier transforms. For example, here I am just giving a typical example of a 2D spatial image. An image is composed of two axes, x and y axis. X and y axis. This we call as a spatial domain. So since if it is expressed in terms of x and y, we say a spatial domain. So that domain is called a spatial domain. Now, this using the Fourier transform, discrete Fourier transform, we can convert to the other forms. We can transform from one form to another form. That is the job of the Fourier transform. So we convert to the sine and cosine components. To convert to the sine and cosine components, you can see the first equation. The small fij is the spatial domain. That means an image is in this domain fi comma j is converted to the capital F k comma l. K comma l is the Fourier domain or frequency domain. So we can convert to another form. So why do we want to convert to the another form? Because satellite image, I said it was very huge image. You have a very high storage. It will take much space. So now you have to compress into a small space. So Fourier transform is used to compress the image. How do we compress? First, the input image is Fij. The spatial image domain goes into the input and it is converted to the sine and cosine form. By converting to the sine and cosine form, the information in the spatial domain is not lost. That is the advantage of this Fourier transform. So without losing any information, we can change to another form which has very low storage capability. For example, a 1 GB image, you can store it in a 100 MB space. So you can put 10 more images in the 1 GB. So in that way, it is much advantageous. Second, if I want to send an image to you, if the image is a 1 GB image, how will I send it? It will take so much time, and it takes lots of bits to transfer. So basically, what I will do, I will just convert to the spatial, to the Fourier domain, frequency domain, and then I will send you. And you can download in the frequency domain, and then you can reconvert it to the original spatial domain. Reconversion is done through inverse Fourier transform, which you are seeing in the below. You can see the e power minus is lost here. This is inverse. You can just, if you invert that, you will just get f of u comma v. Here you can see in this right hand side, you can see f k comma l. K comma l is the Fourier domain, goes as the input, and your output is f u comma v. U comma v and f I comma j are the same, but when they want to make it differentiated, that's why they express in u comma v. So as a typical example, I'll just show a MATLAB application how to compress an image, how to reconstruct the original image. So let us take a simple image. This is a normal image, JPG image, just you can read it. And next, you can change it to the gray levels. And next step, you just apply Fourier transform. Previously, you see the difference. First, this is the input image. You have this. Why this image is chosen? Because it has some spatial heterogeneity. So if you have some spatial heterogeneity, you can easily visible in the Fourier transform of images. That's why I just chose some strange photograph. So basically, after converting to Fourier transform, you just see a blank, white, black, blank. It doesn't mean that there is no data, but still there is some data. But it is in another form. That is why we could not able to see, because this is in the Fourier domain. It is in the frequency domain. It is not in the spatial domain. That is why we could not able to see. It is not comprehensible to our mind. So now the data has been decreased from 1 GB to 100 MB. The compression ratio of Fourier transform for a JPG image is 10 times. You can decrease by 10 times, 10:1. So you can decrease the size. So now it is in the another form. So you can easily send or compress or anything else. Now we just center to see it, and then transforming to log. You can see this is how Fourier transform looks like. This is the image, same as the input image. Previously we saw the spatial heterogeneity image, the same image, but it is something like different. But the information in that image and this image are the same. So now This lag transformed Fourier transform image can be reconverted to the original form, that is which was earlier existed. We can reconstruct to the same image. So this is how it is used in image compression and analysis. I just talked about image compression. There are more analysis. For example, if you see some errors in this image, if you want to remove that, you can just convert. You can just change it to the Fourier form, and you can just pass the low pass or high pass frequencies, and just you can trim it, and you can add it, and you can reconvert. That is why analysis. You can convert to spectral analysis. You can do a spectral analysis, Fourier analysis, and any other analysis. So these things are really required for remote sensing images. There are certain limitations for in terms of remote sensing capabilities, but still it is used. Okay, let us come to the last portion of the lecture, and final atmospheric correction. Previously we saw about the imaging systems, we saw about the data compression, data storage, and how it measures what's the basic things of light. So these things we can easily do. Those who have some understanding about light, some understanding about the programming, you can easily do. But atmospheric correction are mostly done by climate researchers, those who have very good idea about the atmospheres and the earth sciences. So why do we need atmospheric correction? For example, the right hand, the left hand side, you can see some hazy image with almost like a cloud, some hazy image, blue clouds. You can see some particles scattering in the atmosphere, because since the satellite is launched some 700 800 kilometers away from the Earth's surface, it sees the Earth from there. So whatever dust particles, whatever things present in the atmosphere, it will just capture. So we just want to remove all those things. That is, for that we cannot do it. Removal of this kind of errors cannot be done in a normal photograph, but in satellite photographs we can do it. That is why we launch in different bands. If you have more bands, we have more spectral resolution and more radiometric resolution, more easier to do the atmospheric correction. So technical people, they do, for example, who have understanding about aerosols, and all those in NOAA and NASA is mainly doing have the data. So based on their data, we can also do. So we have to learn a bit of atmospheric science so that we can easily interpret the data. And why atmospheric correction is required? Because there are many gaseous particles in the Earth's atmosphere. We have oxygen, we have water, we have carbon dioxide, we have nitrogen, and many other things. So all the components can be removed to bring the right hand side before and after the atmospheric correction. So this is a typical example of how paths, you can see lots of directions, A, B, C, D, like that. All things scattering and back scattering, all this physics you need to know to precisely estimate each parameter and removal. So that kind of idea, even we do in, there are my colleagues, they have been doing lots of atmospheric correction in this IIT Madras. And I'll show how that is done. This is a typical image of the Earth. You can see, just seeing that image, you can see some stripes, some cloudy stripes running from north to south, and something like dust, other things is running. These are all atmospheric particles. How that is made? Let us see this is only the block diagram, block area. Just zoom it. Now you can see these are the clouds. These are the clouds. This is the sun glint, because when the sensor sees the Earth at particular angle, you can see the sun glint. And these are the aerosols. Aerosols means dust. We may think that there is no dust in the air, but still there are lots of dust in the air. So those aerosols should be removed. So removing this, we have a equation, several equations. We have a LT means the total light, and the LA is the aerosol light, scattered that light coming from the aerosols. Light is coming from the Rayleigh scattering, LR. Then a combination of Rayleigh scattering and aerosol, that is LRA, and T is the transmittance, L is the ground radiance, T is the again diffuse transmittance, and here is the sun glint, and this is the white cap component. And similarly, there are many other models to remove the atmospheric component. These are all models published, and these can be used to remove the atmospheric effects. So after correcting all these things, finally there are lots of procedure, and following all those things, we will be able to retrieve the final ground reflectance. This is the topmost is the error signal that is actually captured by the satellite sensor. After correcting all these things, you get the below one. So similarly, that is how the atmospheric correction is done. And after correction, it is then converted from the radiance to the reflectance. And you can see the difference between the previous and after image of a Sentinel. You can see the left and the middle one. What's the difference of atmospheric correction? So once that atmospheric correction is done, then to get the information from the target, algorithm development, calibration, and validation is done to know whether the instrument, the sensor, satellite sensor is performing correctly or not. So based on that, what we do is to validate the satellite measured data, because now we said level 1 to level 4, we have certain values. So now we have to compare whether that values are accurate, whether that is reliable, or it can be used for further work, so that we can we go to the sea. For example, since I am working in the oceanography, I go to sea. If somebody else work in some other area, they go there and they keep on validating. For that, we have several instruments. We measure light. We measure light in the ocean, in the atmosphere, and we send atmospheric column balloons, and I think we measure all those things. After measuring, we get the light signal. Based on this light signal, we do lots of corrections, and we calibrate the. You can see the right hand side, the below image is the radiometers. These are called radiometers. Radiometers are the sensors that capture the photons. It is nothing but the same sensor of the satellite sensor, but this is the size of this instrument is small, but the size of the instrument which is kept in the satellite is something big. Only difference is this is access to us, that is not access to us. This is captured from a distance. This is captured in the particular location. So based on the measurements, we just calibrate the sensor signal to this instrument and the satellite instrument. Similarly, lots of people around the world, so NASA is doing, ISRO is doing, even in IIT Madras we did, and we many people around the world, we are collaborating and we are doing it so that we can get a good accuracy in the data, so that it will be useful for the mankind. After this image algorithm, after developing the algorithm, we just implement to estimate some other physical parameters, so that now you can see because of corona, most governments started funding for the virus studies and also for climate change studies. So climate change regarding earth science studies, remote sensing, they have allocated lots of money. All countries are allocating money for climate change. In that sense, people want to study whether these diseases or these are related to the climate changes or other things, so that lots of funds are there. So based on that, we develop algorithm and to implement to find out whether there is any change or not. What about to the previous decade and the before decade? NASA is doing it since several decades. So similarly in India, we just did one of my team. This is not my work; it's one of my friends' work, and they were doing to estimate and how that is influencing India's climate system. Similarly, you can use the Fourier transform to detect and to separate the things using the power spectral density, and you can separate the features based on Fourier transform. So clubbing everything, finally we do to what strategies are required using remote sensing. What strategies are required to develop, or what we have to stop, what we have to monitor, what are the things have to do. Common is interested in always doing that, and most people are doing that. So this is an overview of remote sensing, and how I have just told how remote sensing is, how remote sensing works, how it works in terms of sensor, how images, what you can contribute. And based on this lecture, I hope that you have understood what kind of things you can do to remote sensing. For example, if you are good in programming or if you are good in images, if you like images, you can simply download satellite images and you can work on and you can bring up something fruitful, and it can be useful for the mankind. In terms of instrumentation people, you can also design a high resolution and imaging systems for the future or the upcoming and all these things. So basically, I hope that this lecture would have been a good lecture for you, and I hope you have learned basic things of remote sensing. And I'll be happy if somebody have some ideas to bring up something in terms of in terms of image processing or something. I'll be happy to collaborate, and you can send me email, and so that we can discuss. And if you want to make up a publication, so we can think of. So kindly please contact me, and if you have any doubts, you are glad to ask any questions. Thank you very much.
Praveen?
Yeah.
Thank you, Praveen. That's a nice presentation. So some questions are there in the chat box. You just go through that and they can answer now.
Okay. I'm not sure. I couldn't see. I cannot see anything. Where can I see that?
You can stop sharing the presentation.
Okay.
At the top, you can see the chat. Have you seen that?
Yes.
Yeah. So just scroll down.
Yeah, I'm scrolling down.
Starting from Vignesh Shankar.
Okay. What type of role is played by programmers on remote sensing? Yeah, it's a good question. Recently, when I come for postdoc, I saw lots of opportunities for programmers, because previously, for the last decades, people were interested in working on climate science, but they had a limited number of data. Now, since lots of satellites have been launched, now people are less to work, because manually you cannot work. So if you want to run a bulk of data, so you need manually do. So the basic concepts you have to develop, all these concepts you have to convert, all these mathematical forms has to be converted into programs, and so that it will automatically process and it will be automatically shared to the researchers and shared to the community. So in that way, programmers can be much useful. But main thing is algorithm development, software development. Normally, since satellite images have a bulk of data, it cannot be just processed with a small kind of softwares. It's like MATLAB. MATLAB can also do, but there are some limitations even in MATLAB. So there are separate softwares. For example, NASA has developed some software called CDAS, that is for ocean applications, and the European agencies have developed a Sentinel application programming toolbox. So there are many opportunities for programmers in remote sensing. You can develop algorithms, you can convert all mathematical equations to the day-to-day applications. So in that way, programmers can be very useful in remote sensing. And if you have a very strong knowledge, and if you have a strong knowledge in physics, then you can look for opportunities in ISO also. And if you are interested for PhD research, and there are a division in IIT Madras, you can also apply. And if you want more idea, if you have a gate, then it will be great. Then if that is the case, you can email me. I can tell you what can be done. So next. So next, images from you.
Above.
About?
Some more questions above. Just scroll up.
Okay. How to detect oil spill using remote sensing techniques?
At the top, you went down.
Down?
No. Vignesh Shankar, the question is, why do the satellites are not working during sunstorms and how vulnerable a satellite can be?
Generally, yeah, because sandstorms backscatter light too much. Even not only light, it attenuates. Attenuation of that is electromagnetic radiation is much high during sandstorms. That is why we don't get. Actually, I did not see the question. Actually, where is the question? Nicholson, can you read the question once again?
Yeah, why do
satellites? Yeah, I just saw. Why do the satellites are not working during the sunstorms? So I didn't understand what is sunstorms. Sunstorms means, are you talking about sun flares? I think he's talking about sun flares. Yeah, sun flares. Even for example, this eco sensor have been destroyed by the sunstorms, because in electromagnetic radiation, not only in the optical wave band, it also emits in thermal and other regions. That will affect. That is why when testing in, for example, before launch, they used to test in extreme conditions, extreme cold, extreme heat, extreme radiation. That is why they test it. If it fails in the testing, ISRO test, NASA tests. Before that they test. So after testing they launch. So sometimes, every time that does not happen, that does not go smoothly. So sometimes it happens. Sometimes sun flares will affect. So anyway, that is not into my domain, but definitely somebody who is working on instrumentation and regarding these things can answer very precisely. And next, please give details on data sets where to collect temporal data of a particular area. There are many satellites. For example, if you are working on optical thing, there are Landsat and Sentinel satellites. You can Sentinel satellites cover every month. At least you will have 5 to 6 images. Landsat you will have at least 2 images per month. So you can register in earthexplorer.com. You can type in Google Earth Explorer, if that so that you can register there, and you can click Landsat or Sentinel according to your preference, and you can select your study area and you can download data. So only thing, you give your information as academicians research, so that they will give you more access to the data. So you can download. Temporal data means by days, so you can easily get. Which satellites are preferable for land use and land cover classification? You can use Landsat and Sentinel-2, Sentinel-2 A and B. So Landsat you have spatial resolution of 30 meter, and Sentinel-2 you have spatial resolution 10 meter for red, blue, and green, and other for 20 meter. So Landsat and Sentinel are more preferable for land use and land cover classification. Images from USGS, EUROS are not available as open source, from where we can acquire images directly for our research purpose. Yes, there are limitations for in some cases, but I think mostly Landsat and Sentinel would help for in optical ranges. Even Sentinel-1 image you can download for microwave data, so that can be also, that is freely available. You can just check in the internet. Just go to earthexplorer.com and you will find. You can download. Is there any alternatives for remote sensing? Alternatives, I'm not sure in what sense you are asking, but in terms of image capture, I don't know.
Okay, you can skip that question.
Okay. Yes, how to detect oil spill? Yes, definitely you can detect oil spill. Oil spill, there are two methods. Even oil spill can be seen in optical and as well as in microwave. Both sensors can give. Even Landsat can give, Sentinel can give. Only thing is there should not be a cloud cover For example, equatorial region you have more cloud cover, and you go to latitude, higher latitude, so cloud cover is relatively less, so you have more data. And microwave data you can check for Sentinel 1. What's the role on deep learning algorithm in remote sensings? I don't know much into that, but there are now artificial intelligence, although is booming, because if, for example, one of my friend was working on SAR techniques to detect ships. So what if an enemy ships comes in? So there are satellites that keep continuously monitor the region, so that if there is any changes, so by training some data, they can find out. So in that way, artificial intelligence are much using are used in remote sensing. Which satellites are preferable for change detection prediction? For a land-based, you can go for Sentinel 2. Sentinel 2 is is the best one. So if there is no images on Sentinel 2, you can go for Landsat, but definitely you will be getting for Sentinel 2, no doubt. Sentinel 2 is the most recent satellite, and you have high spatial resolution, so that you can use that. Have I addressed all the questions?
Yeah, that's.
I think
addressed all the question.
Huh?
Yeah, you have addressed all the question.
Yeah. Thank you.
Okay, wait, Praveen.
Yeah, sure.
Someone asked to refer the book. Which book? The book name for reference.
For basic remote sensing, you can use Lely Sand book. Lely Sand, Interpretation of Remote Sensing. That is one of the most common book used by remote sensing scientists. Plus, there are few Indian other books also. Yeah, but you can refer. Lely Sand is most quality, and you can understand most physical concepts.
Okay,
I would suggest that book.
Okay, thank you for your presentation. That's a nice session. Now I request Dr. Murugan, Assistant Professor of Physics, to deliver the vote of thanks.
Good evening to all. I am Dr. Murugan, Assistant Professor in Physics, Department of Science and Humanities, National Engineering College. First of all, we sincerely thank our management, director, principal, and our HOD sir for giving this opportunity to organize this type of webinars. And we heartfully thank Dr. Praveen sir for his valuable explanations. In remote sensing, he delivered really an informative lecture, which was from the fundamentals to applications. And he beautifully connected the physics, maths, programming, and other basic science with remote sensing technology, especially the significant role of Fourier transform in image processing. Student might understood the significance of basic sciences and programming knowledge through this lecture, and hope all of us get some remote sensing knowledge through this lecture. Thank you, Praveen sir. Thank you for your fruitful discussion also. And I thank all the participants for his patience learning and asking some questions and make the discussion fruitful. Thank you all. Once again, I thank you all. Thank you.
Okay, thank you, Praveen.
Yeah, thank you so much, Dr. Nicholson.